Good morning to the chair of Iconita, Professor Chaudhry, the moderators. I think it's Professor Hussain and Dr. Chakrabarti. My name is Portia Felix, and I'm from the Department of Civil and Environmental Engineering. My research is entitled The Underwater Trajectory Behavior of Heavy Oil Jet in Crossflow from a Broken Surface Pipeline. You all see, right? Right, good.
Yeah, can you put it on the slide presentation mode, please?
Oh, sorry.
Good, thank you.
Right, okay, good. Right, so the outline of my talk this morning, which will be short, is I will introduce the topic and discuss the state of the art in the modeling of underwater movement of oil. I will show the model that I have derived and the numerical results that I have obtained, and then I will state the conclusions and end my presentation. So a positively buoyant surface discharge oil jet occurs when a lighter or dense or less dense, faster moving fluid is discharged downwardly into a heavier or denser, slower moving fluid. For example, heavy crude oil, which as we know should be lighter, can entering into the seawater, which is denser and a slower fluid ambient. Now, in such a case, the oil is expected to rise almost immediately to the surface due to buoyancy forces. However, in this case, it was observed that the oil became trapped at a shallow water depth and moved horizontally, as shown by the diagram. And so this odd oil behavior allows us actually pose the question of what was the mechanism that allowed it to form that horizontal column of heavy oil to be suspended at a shallow water depth in the water column, as opposed to rising to the water surface, which is what is expected. And in this case, it is also a surface oil spill. So usually we know that surface oil spills are usually deposited on the water surface. Usually if there's an accident or if there's a leak, you have oil on the water surface. And the downward movement or the underwater movement of oil is in the form of oil droplets. And this movement is called the vertical dispersion. So the vertical dispersion of the oil hinges on the theory that the wave motion breaks up the surface oil spills, oil slicks into oil droplets of various sizes that is then transported vertically or entrained into the water column. However, as you recall in the previous slide, this did not happen at the water surface. You actually have water, the oil being penetrated into the water surface. So the state of the art for water surface oil spill modeling really involves a very common analytical equation that you see there, that is used to determine the movement of the oil droplets throughout the water column. So the equation actually represents I have each term and I label them. So SCOV will be the coverage of the oil on the sea surface, your dispersion size of the particle, the oil droplet particle. And then we're looking at the rate at which the oil is moving through the water. So this equation is used, as this empirical equation is used by many authors to determine the movement of oil in the underwater movement of oil. However, so the modeling approach for that particular model is that it is based on the Lagrangian particle approach. The method represents the transport of a surface oil slick as a large number of individual particles, and so their discrete path and mass are followed and recorded as functions of time. So that is how that equation works in current models today. So to compute the movement of the oil droplets in the water column, some oil spills use the random walk technique to follow the motion of the individual droplets. And some models mention an analytical fit method to model the vertical dispersion. However, I've decided to try to work at using a numerical approach, seeing that my flow situation is different. I'm not looking at oil droplets. So I have derived an using the Navier-Stokes equations. I've derived the continuity equation, the x momentum, z momentum, and transport equations, as you would see on the screen. So this mathematical model now will represent a flow field that is subjected to a temperature gradient, a density variation generated in the flow is due to the buoyancy forces, therefore causing inducing the motion in the fluid. I follow the method of the projection step method done by Corin and Timan in 1969, and I've used that method to guide the numerical modeling approach using MATLAB. So it really is made up of three major steps. I will compute an intermediate velocity field, then I put a computer pressure and update the pressure as I go in each time step using the Poisson equation, and then I will get a new velocity field, and it's iterative. So this thing, those three steps are iterative steps that will allow me to view the velocity field of the oil underwater, which is treated as a mass. So to verify my model, I did a benchmark model where the flow is differentially heated in a rectangular domain. So at the base, I have a high temperature, and at the top, it's a lower temperature. And I've allowed the model to model this this benchmark flow in this way. So to show you how it works. You can see the model. So it depicts what it can handle the benchmark. It shows that the model can handle the benchmark model. Right. Another simulation that was done now. So this I'm applying it to now the situation that I'm modeling, which is the oil becoming suspended in the water column. You can see I have the opening, so that will show the oil is coming. If you remember the diagram shown above, as the oil enters into the water, it's becoming suspended by the red concentration there. And it's moving horizontally. So the model shows, or has the potential to show, that the oil can become suspended underwater. And this was just another model doing the same thing, just at a faster rate. You can see it come in, and the oil is this patch here that's going across. So it shows satisfactory results of the numerical solution of the 2D buoyancy-driven model when compared to the results of the standard benchmark. However, but model sufficiently demonstrates that the oil can be immediately pushed beneath the water surface due to a momentum force, because remember, it's coming out from a broken source, and be suspended underwater and travel horizontally. And this behavior is because it illustrates the suspension of most of the oil underwater in shallow water depth without a significant amount of water going to the sea bottom. And so this suggests that density changes between the oil and the water in the column creates a sensitive density layer that allows the oil to remain suspended. So what happened is neutral buoyancy. So basically it remained underwater because of the changes in density in the water column that allowed it to become neutrally buoyant. So that can answer why it became suspended and not float to the surface. That's it. Thank you very much.
Thank you very much, Ms. Felix, for that very, very informative presentation and using the graphics to show it also. There's a question by Professor Dimitri Eskin from the Department of Chemical Engineering.
Okay.
He mentioned that it is difficult to see from the equations shown how you accounted for two immiscible phases. Could you briefly explain this?
Oh, okay. That is correct. This is an initial model where I did not look at my immiscible phases in that level of detail. What I did was I looked at temperature difference and the speed of the oil to make the differentiation between the oil and the water. Further work, and I have done it already, looked at the phases.
Okay, thank you very much. Any questions from the attendees, and participants? Any more questions? If not, I'm pretty sure there will be many questions that you will receive by email.
Okay.
And thank you once again very, very much for taking part and